All righty, everyone. My name's Edward Tahmizian. I'm one of the board of directors of Internet Infidels, and I'm on their kiosk editorial review committee as well. And I have a library piece on the origin of evil. And today I'm going to be interviewing the legendary Bill Gaede. Thank you for being on the show, sir.
Yeah, no problem.
All righty. And before we go into the interview questions, did you want to tell us a little bit about yourself and your biography?
Well, yeah, there's not much to tell, or maybe there's too much to tell. I don't know which way you want to look at it. Yeah, I've ran into trouble because I got into politics. And to make a long story short, I ended up in prison, as many people know out there.
Uh-huh.
And after I got out, I left all that shit behind.
There you go.
My recommendation to anyone out there: never get into politics.
Gotcha. All righty.
And that was my problem.
That's all right. All righty. Okay, so to go into the first question for today, what is your rope hypothesis, and what are some of the problems with the standard model of light, like the wave packet?
Yeah, I guess we got to start at the beginning, and that's a big, long introduction because
Sure.
If you look at mathematical physics today, right? Just any branch, whether it's general relativity, quantum mechanics, string theory, or even the dissidence, people like the electric universe and the John Chappell Society, all these people, they have irrational explanations for almost any physical phenomena. Almost any physical interpretation is irrational today. Why is it irrational? It starts, I think, like 3 centuries ago, 4 centuries, and I'm going to cover it year by year. Okay, by the way.
That sounds good.
No, but if you go back, what happened in the 17th century, known as the 17th century so-called scientific revolution, they abandoned the Greeks. And what they did, they moved on to something new, which was, hey, do experiments, measure, get some equations, and then we will be able to figure out how this universe works. The problem with that was that the how had to do with descriptions and not with the why, with the causes, with what is the physical interpretation for how the universe actually works, meaning what is making it do all these things. And the issue here is that with experiments, you are not able to determine something which is invisible and intangible. If we go to the lab, you can measure whatever is visible and tangible. You cannot measure that which is not. And the problem here is that Mother Nature runs her world, or Father Universe, God, the devil, whoever you want to pray to, right?
Yeah.
They run the universe with invisible, intangible mediators. And so we're not going to be able to discover them through experiments. And all you can do with measurements is measurement what is seeable and touchable. You cannot measure that which is not seeable and touchable. And what they did, really since day one, and they always used particles as a simulator for all these things. They said, it's done with particles. And then in the 17th century, they came up with waves. Robert Hooke was the guy who really came up with waves. He wrote his book, Micrographia, in 1665. And that's when the wave theory started, handled later on, a little later by Christian Huygens, from a Dutch guy. Okay, so they came up with a wave theory. But see, both the waves and the particles are one-way mechanisms.
Yeah.
They only go one way. They come out of something and go.
Okay.
Well, the problem with that is that you can simulate push, but you cannot simulate pull.
Yeah.
And so what's missing today in all of mathematical physics, what is missing today in the dissidence, is pull. We do not have the force of pull. We do not have a mechanism for the force of pull. And so if you want to pull, you have to have an extended entity. Okay? And if you want to pull on a donkey, you don't throw stones at it. You have to tie a rope around its neck, and then you can pull. You know, so that's, if you're going to give a physical interpretation for action at a distance phenomena, such as entanglement, such as gravity, or any of those, you're going to need to put some mediator that pulls. And that's where mathematical physics is lacking. And the reason it's lacking, we go back to the 17th century, it's that they said, we're going to figure all this out by doing equations, measuring, and doing experiments. And here we are 400, 300, 400 years later, and what we have is a particle can be at two places at once. A zero-dimensional singularity is known as a black hole, and that pulls on a star, which is billions of miles away. And we have Big Bang, which is the creation of space and matter. So what existed before? Well, that's an unscientific question. And so on. You know, they give you the runaround, and you say, what have I learned? What do I understand about the universe? And when you put all these people against the wall, they say, well, that's philosophy anyways. Go to the philosopher. Go to the other side of campus and ask the philosophers of science. You go there, if you take the trouble, you go there and they say, oh, we get our cues from the mathematical physicists, by the way, you know. so it's a runaround.
Tell you to go back,
Okay, but James Maxwell essentially established that light has some kind of vibration, some kind of wave. It's some kind of wave phenomena. And he got that first from Faraday, and even before that from French guy, what's his name? Augustin Fresnel. Okay? Augustin Fresnel, he essentially came up with this wave. He developed the wave theory, and from there on, for the 19th century, it was all wave theory. James Maxwell put some equations to describe all that. And today we have that description. We have some description that light is some sort of wave. But when you look at the wave of mathematical physics, what you find are vectors. You know, all those things that are moving, they're little arrows. And you say, well, what are those little arrows? Well, those are vectors. What is a vector? Magnitude and direction. So that's what's moving, just magnitude and direction. What's magnitude? A number. So you have the number 5 pointed in some direction, it's moving. In other words, again, it's a mathematical description. That's what you're staring at. But they had to put something in front of your eyes to say, you're staring at a wave. Okay, what is that wave? It's just a bunch of numbers. What's a field? Bunch of numbers. What's a magnetic field? Bunch of numbers. What's an electric field? Bunch of numbers. What's a gravitational field? Bunch of numbers. And so all we have are descriptions. Mathematics can only describe. Now, what I say, what happens if we replace the famous wave with a rope? Okay, now here's a 2-strand rope, okay, and I'm saying that, assuming my 2 fists are atoms, right?
Okay.
I'm saying that this rope, if it torques, the torsion on a rope is what light is. It's not a flow of particles. It's not the waving up and down or in any way of a transverse wave, which is a bunch of vectors. No, it's a physical rope that binds any 2 atoms. That's my starting point. That's my assumption. So once we have this assumption, at least now we have a physical entity, right, that can produce action at a distance. But what's the issue here? The issue here is, first, we're talking about a physical interpretation. Second, we're not saying, look, I'm going to give you a bunch of math and equation. No, we don't care about that. We're saying, how does Mother Nature do it in real life? She never went to school. She doesn't know what math is. Okay? We invented these relations. Okay,
True.
You want to know how she runs her universe, and if she has planets like the Earth and the Sun, she works with objects. She doesn't work with equations. So you have to explain, why does the Earth fly out of the solar system? How does an atom affect another one at a distance, et cetera, et cetera, et cetera. And for that, you need physical objects. And so we get rid of all the math. We get rid of all the equations. We don't need them because we're not going to be describing, not because they're not useful, but we're not going to be describing. We want to explain. In order to explain, in order to get to a physical interpretation, I need to put objects. And so I put an object. I'm saying light is some sort of entity, elongated entity, and I'm saying if we simulate it with something that looks like a rope, a 2-strand twine thread, a pair of threads, then you can imagine torsion along this thread, this twine thread, this rope as I call it. And one of the things you realize that torsion is the fastest type of wave imaginable.
Yeah, true.
If you look at transverse waves, if you look at longitudinal waves, the torsion wave leaves them both biting the dust.
Uh-huh.
So I'm saying, look, an atom expands and contracts as Niels Bohr discovered his quantum jump.
Uh-huh.
It expands and contracts. Then if we assume that the atom is a ball, not a little tiny bead circling a nucleus, but an actual membrane, a balloon that encapsulates something inside. We don't have to go into any detail there, but it encapsulates something inside. Well, you can imagine this membrane expanding and contracting, torquing the rope while it does so, and sending that signal to another atom down the road. Uh-huh. Meanwhile, all atoms are interconnected, physically interconnected. Now you can explain action at a distance. The only issue we have to resolve now is where we should have started in the first place, and that's that physics cannot be done without an object. The problem is that we've always misdefined the word object. Everybody, if you look it up in the dictionary, if you ask anyone, people say, well, an object is what I can see and touch, because that's our everyday experience. We see, touch things. Okay, this I can touch this, so this is an object. I can touch the table, it's an object. I can touch the wall, it's an object.
Yeah.
But that's not what it is for the purposes of physics, because there are objects we cannot see or touch, and they are still objects. We cannot see the air. And you say, was the air an object? It sounds kind of weird in ordinary speech, but it has to be treated that way because air is made out of atoms. And I'm touching an atom here. And I can't see or touch it, but there's something there. We call it an atom. We work with that. We say there's a bunch of atoms here that I'm breathing. Something's going into my nose. I can't see it. So is that not a thing? I can't see the chair that's on the other side of the planet in China. Is that chair, the guy that's sitting on that chair, is that chair not an object?
Yeah.
So we can't use the see-touch criteria, which is what's used in ordinary speech. For physics, we have to use that which has shape.
Yep.
When you define it that way, all objects in the universe share one common property, and that is shape. They all have to have shape. There's not a single object anyone can imagine that does not have shape. So what does that mean? That means that this rope is an object because it has shape, not because you can see or touch it.
True.
So when people say, why can't I see the rope? Why can't I touch the rope? Well, now you have an answer, the first answer. There's more than one answer to that. But now you have your first answer. You have the wrong definition. An object is not that which you can see and touch. An object is that which has shape. The rope meets that definition. And so, that's our starting point. That's our assumption. And from there, we're going to build the rope model of light and gravity, primarily those two, including magnetism, electricity, and the workings of the atom.
Sweet. All righty. Thank you.
Long introduction, long-winded, but I had to do it.
Hey, no, that's all good. Yeah, so people can get familiar, with your ideas and stuff. That's good. All righty. So going on for our second question, how do magnets attract?
Okay, that's sometimes they say a picture's worth 1,000 words. A movie is worth 1,000,000 words. Unfortunately, I didn't know what question you were going to ask me in advance, so I could have prepared some props. I do have videos on this, but let me just see if I can explain it the best way possible. Here you have two magnets, okay?
Gotcha.
Those two little dark things, they're magnets, and you can see, that they stick to each other, okay? Typical magnet. Okay, so the question is, again, we can't see or touch what's in between them. The second thing we notice is that when I put them close to each other, nothing is pushing on my hands from the outside. I'm being drawn from the inside. I feel the pull from the inside.
Yeah.
So this is some kind of pull. It's not a push mechanism, because some people want to do it with particles. And it's not, I don't feel anything pushing my hands. I feel already drawn.
Yeah.
And I'll give you another analogy, which falls in here. Okay. Stretch out your hands, and, nothing is pushing on my arms, but I feel them like gravity is pulling them from below.
Yeah.
Gravity is a pull mechanism. We always talk about the pull of gravity, but then they simulate it with particles, which can only push. So we have a contradiction. So we have to face the first thing, and that's that this is some kind of pull.
Okay.
Right? This is some kind of the attraction. Is
yeah, that makes sense.
Obviously, if you have different polarities, they push each other away. But I mean, the attraction is some kind of pull because I can feel it pulling from the inside. But as you can see, you cannot see.
Yep.
There's nothing there. I don't smell it other than the air. I could do this in space. It would work also. And the question is, there's nothing there I can see or touch. So we have to forget, first of all, about see and touch.
Yeah.
Okay, so now we have to discover what the mechanism is. And you've seen the standard iron filings spread around magnets. And there's two types. Again, picture's worth 1,000 words. All I can do is simulate it with my hands now.
Yeah, that's all good.
If I want to push these two hands apart, imagine they're swinging like two rollers moving in opposite directions, or maybe the paddle wheels of two river boats. Okay. The river boat has these big paddles. Imagine these paddles moving in opposite direction. So they hit each other and tend to push each other away. What happens if they're going in the same direction? Well, as one comes up, the other one comes down, they latch onto each other, and that's where you have the pull mechanism. Okay, so I'm saying that when you have two magnets like these that attract each other, what you're having is something that's moving, which we call the magnetic field. Something is moving in that field. James Maxwell said, in that region, there is matter in motion. He said it. And we forgot about that, but there's matter in motion, some exotic matter that is in motion. Okay, so you have this one coming up, this one coming down, they latch on each other, you have pull. What happens when you turn it 180 degrees around, like north to south pole? Now you have the opposite effect. Now you see why they push each other away. So we have the mechanism of attraction and repulsion. The next question is then, what's in there? What's in that invisible area? And what I'm saying is, it originates in the magnet. We all, I think, will agree on that. Whatever it is, it originates in the magnet. You can't have a field, a magnetic field, without the magnet. You got to bring the magnet together. Yeah. And so, if we had the eyes of God and we could see and touch in that region, I think what we would see is a bunch of threads moving in one direction, the other one moving in the opposite direction for attraction, and both sides moving in opposite directions, the threads, countless threads, pushing each other away. What are those threads? The threads that come out of the rope. When I'm saying that Mother Nature, or Father Universe, the devil, whoever, what they do, the way they run this world, especially in the magnets, right, is you have all these domains in a magnet. When they are aligned, that's when you have attraction or repulsion. If you don't have them aligned, all you have is a piece of iron. Okay? That's it. But when they're aligned, we call it a magnet. And why are they aligned? What do we mean by that? I'm saying that we have rows of atoms, really molecules, but it's easier to conceptualize this with atoms. Imagine hydrogen atoms, right? And they're all magnetized. What do we mean by that? They're all aligned. They're all merged together. They all move simultaneously. What's moving? What's scrolling around? The threads that make up the electron shell, the electron membrane, and also the ropes that interconnect them. So if you have these threads moving around, countless threads, we can explain the so-called lines of force that Mr. Faraday noticed in 1830s.
Awesome.
And that's essentially in a nutshell. Again, a picture is worth 1,000 words. A movie is worth 1,000,000. If I could show you the movie, you'd say, "Oh, I see what he's talking about."
Awesome. Yeah. And for everyone that you can go into Bill Gaede, he has a YouTube channel and he has a video on that, so you guys can check that out for further details.
Yeah, I have several videos on magnetism. Yeah.
Sweet. Alrighty. And then for our last question, this is the one I'm really interested in. Could you tell us about your life as a spy back in the day? Because I remember it was a pretty big deal when you were like on Fox News and everything, and I was like, dang.
Yeah, it was some great days, in my youth. I mean, I'm going on 69 now, but this was when I was in my 30s, 30 years ago. But yeah, first of all, it's, you're born with, or not born, but you're raised with some ideals or you grow into them and you make your own ideas about the world. And so I had these ideals, and I entered the Communist Party at the time. And because of that, when I came to the States, I decided to use my position in these companies to try to help the Eastern world. In other words, the communist world, because that's the ideal you come with. Okay. And so what happens after a while, it takes time, but you finally realize that it's not worth it, that something's wrong in your reasoning. But until then, what we did was, we took material and we gave it to the Eastern Bloc at the time during the Cold War.
Okay.
And because of that, I got into a lot of trouble. Turned myself in, by the way. I turned myself in to the CIA first.
Okay.
They put me in contact with the FBI, and we worked for about 2 years. And, just trying to infiltrate the Cuban, in this case, it was the Cuban intelligence service. They're what is called the Ministry of the Interior. And, they got some names, that sort of thing. And what happened was, in between, we had these companies, AMD and Intel. They figured out what we were doing, more or less. The FBI cleaned their hands off of me, and I had to run for my life.
Oh, man.
They caught up with me. We agreed, I plea bargained with them, and they gave me a very lenient sentence. And after my time was done, I got out of that. But even before that, I had lost my ideals completely. And today, all I can recommend to people who get into politics, you have people from the right, people from the left, they have their ideals and how the world should be run. If you can't do anything about it, forget it. Just turn your TV off.
Okay. Yeah.
That's the safest way. It's very exciting when you're in there, but what these governments do, they sacrifice sometimes upon here, upon there, because at some point, maybe it's not convenient for them anymore. And those decisions are taken by the heads of the intelligence services. And, you got a person out there who's doing something, and they say, well, turn this guy in because for whatever reason. And the guy may not even know it, but they turn him in. They say, well, he's a small pawn, turn him in. They do this stuff. And so and when they turn one guy over, or when one guy, comes out of a country and leaves and goes to work for the other country, that guy knows a lot of spies. And he said, oh, by the way, this guy's a spy over there and this guy's another. And they turn spies in. They go after these guys. In some countries, they execute them.
Mm-hmm. Gotcha.
I mean, a lot of these, so spying is a bad business. Never get into spying, and also never get into politics.
Yeah. It's much more grueling than the James Bond films. It's not as exciting. Well, you have your excitement, but then you have your danger, but more so on the danger side, I guess.
Yeah, what I miss is all the girls that they offer you.
Yeah, you don't get any girls.
See, James Bond took all these beautiful girls, and you go around without. You just got to do your work,
By the time he got in, there were the CIA people.
Where are all these girls that they promised me?
You're on your own. Like, dang it! That's the only reason I joined.
Yeah, and they say you'll see them in spy heaven.
Yeah. Oh man. Oh well, yeah. Well, thank you for answering all those questions. And then So one more thing. So there's a movie out there called El Crazy Che, and that's basically about your life as a spy and stuff.
Correct. Yeah, it is. Pretty much it covers most of what I did.
Sweet. And is that on your YouTube channel by chance?
I'm sorry?
Is that on your YouTube channel? The movie?
No, it's the only place that I can find. I don't even have the movie. I watched a couple times, but it's on the Amazon. What is it? Prime.
Amazon Prime. Okay.
It's on Amazon Prime.
Okay, so people can check it out there. Awesome.
Yeah. Absolutely.
Awesome. Alrighty. Well, thank you for answering all these questions, sir. And then by the time